Hello student to the course of physics of linear and nonlinear optical waveguides. So, today we have lecture 11 and today we will going to continue the concept of ray equation and try to find out the ray path for a graded index profile. Lecture number 11. So, ray equation is continued. The continuation of the previous concept ray equation. Well, what was the ray equation? Let me write it once again. If I have z and x, a two dimensional refractive index variation like this, if the profile is given, then based on the profile a ray will follow certain path going to some point A to B, and I can have a differential equation which tells us how the ray will follow the path, and this differential equation was something like d2 x dz square is a function of z is equal to 1 divided by 2 of beta tilde square. This quantity beta tilde is a ray path constant, we know that, and this is a constant quantity, equal to d n square x dx. So, that was our ray equation, and we will going to use this equation to find now a different in the previous class we find out the condition for the path for graded step index profile. So, that was the step index profile, and we find from this equation that the rays are moving in a straight line like this, and the expression was x function of z is simply, if this initial angle is given theta 0, then tan theta 0 multiplied by z, a simple expression like this. If I launch, by the way, if I launch the light in other point, suppose here, then I need to add that as well with the boundary condition. Suppose I launch a light here, so it can also follow a straight line path, but I need to add something. It is like the b is not equal to 0 in this case. In this case, the constant b is not equal to 0, as simple as that. You just need to put the boundary condition and find it out. However, today we will going to find the ray path for a parabolic index profile. This parabolic index profile is not new, I already introduced this in one of the classes, previous classes, and the profile looks like this. Along this direction it is suppose n square x, this is the direction of x, and mathematically it was n square x is equal to n1 square 1 minus 2 of delta x divided by a whole square for this region and equal to n2 square for this region. That was the mathematical definition of the refractive index profile for this parabolic structure, parabolic refractive index profile. Now, I know what is my n square for this profile and I need to find out how the ray path will look like. Ray equation is in my hand. So, let me write down my ray equation once again. So, my ray equation, make it red, my ray equation is d2 x dz square is a function of x is equal to 1 divided by 2 of beta tilde square d of n square x then dx, which is this one, and now n square is given as a function of x. In the step index profile it was constant, but here you can see it is not constant anymore, it is a function of x, x is sitting here. So, it is a function of x. So, first I need to calculate this. So, d of n square x dx, if I make a derivative of for x less than a in this region, if I make a derivative, then this is minus n square is here. So, this derivation, the derivative becomes simply minus of 4 n1 square, because this 2 and then due to this derivative I have 1 2. So, this is 4, negative sign is there, n square is here, delta is sitting here, a square is also constant. So, it should be simply delta divided by a square and then this quantity multiplied by x. So, this is a function of x. So, this x will be there. So, I can put it here in the ray equation. So, the ray equation becomes d2 x dz square will be simply 1 divided by 2 of beta tilde square and this quantity d2 dn square dx, I just replace this here whatever the value I got. So, it should be minus of 4 n1 square delta a square and then x. This portion is constant. So, whatever. So, let me simplify this. This is minus of 2 of n1 square delta divided by beta tilde square a square. This entire term is a constant term multiplied by x. So, I can simplify this differential equation and this differential equation becomes d2 x dz square is equal to minus of say k square, which is a constant x, where my k square is simply 2 n1 square delta divided by beta square a square. This is my k square. So, I have a well known differential equation. This differential equation is well known, and we know that for this differential equation one can expect a sinusoidal solution. So, I can readily write down the solution here, one can readily find the solution here, and it looks like this: a constant a sine of kz plus B sorry, B it should be cos of kz. So, this is a general solution, this is a general solution. So, I have a general solution of this differential equation. Now, the next part is to put the boundary condition to evaluate the value A and B, that is all. Again I will going to draw the structure. And here the profile. This is a parabolic profile. So, this is n square as a function of x, and along this direction I have my x, and along this direction I have z. Since it is a sinusoidal kind of wave, I can launch the wave exactly at this point, and if I launch here, it should follow a path like this. Now, note it, here I launch this stuff at 0 0 point, this point is 0 0 at origin. So, one boundary condition, boundary condition one is x at z equal to 0 is equal to 0. So, here if I put that boundary condition, I can have x z equal to 0 is 0 plus b into cos of 0, I should not put degree, it is simply 0, which is 1, this is 1. So, I can have readily b, so this quantity is 0, so b is equal to 0. So, I simply have x is some constant a sine of k z. So, it is simply a sinusoidal wave. If I launch this wave exactly at this point for a parabolic structure, then it should follow a sinusoidal path. A very interesting thing that I find. For step index fiber it was a straight line, but in parabolic index profile, this is a parabolic index profile. So, the path that will going to follow is sinusoidal in nature. So, it should be simply like this for graded index. Now, again another boundary condition. So, this is the amplitude, A is the amplitude of this sinusoidal wave. So, I can also find out this amplitude A in terms of another boundary condition. So, exactly in the previous way, if this angle is theta 0, then I have second boundary condition that d of x dz at z equal to 0 point, that means at here is simply tan theta 0. this quantity, if I calculate from whatever the expression I have. So, now my x z is a of sine of k z. So, if I make a derivative with respect to z, it should be like a of k of cos of k z, and I want to evaluate these things at z equal to 0. At z equal to 0, this value is simply a k, and that thing at z equal to 0 according to my boundary condition is tan theta 0. So, I can figure out what is my a with this boundary. So, my a will be simply tan of theta 0 divided by k. So, in totality my path will be something like tan theta 0 divided by k sine of k of z. So, I can have a set of sinusoidal wave. By the way, k value I should also write it. So, k square is what I calculated here. So, let me go back to the value, it is 2 n 1 square delta divided by beta tilde square a square here. So, it is 2 n 1 square delta divided by beta tilde square a square. So, my k is simply n 1 divided by beta tilde a, then root over of 2 of delta. This is my k, and beta tilde by n 1 can also be written in terms of theta 0, because I know that n of x cos of theta x is beta tilde, that we know. When we launch the light, if I go back to the picture once again, the ray will follow this kind of path. So, here this initial angle is theta 0. So, and this value, the peak value, if I draw the parabolic profile, so at this peak value it was n 1. So, n 1 cos of theta 0 is equal to beta tilde, because beta tilde will be same for all the points. It should also have the same value at this point, which is the origin 0 0. This is x and this is z. So, this condition is also valid at x equal to z equal to 0 or x equal to 0 point. So, my k, I can write my k as n 1 divided by beta tilde, I just replace to the function cos theta. So, it should be root over of 2 delta, then cos theta 0 divided by a, that is my k in terms of theta 0, because my goal here is to find everything in terms of theta 0, because theta 0 is a initial angle that is given to me. So, tan theta 0 divided by k, that term we had earlier, tan theta 0 divided by k, which is a. So, that thing will be simply, when I put the value of k, 1 cos theta will cancel out. So, it should be sin theta 0 multiplied by a divided by root over of 2 delta. So, my final expression for the ray x z is equal to a divided by root over of 2 delta sin of theta 0 sin of k z. So, it should be a sinusoidal wave, it should be a sinusoidal wave, but at the same point it should have an amplitude here, and this amplitude will depend on the initial value of theta 0. If I change my theta 0, I have different paths. So, let me draw finally how the path will look like for a parabolic. So, I need to draw, okay, this drawing is slightly, I need to make it better. So, this is the profile I have. And here at this point I have n1. So, this profile is, this is a n1 square x profile, parabolic profile, and the path the ray will follow is this. This is one path the ray follow, another path, let me draw it another line, and another path it can follow, something like this. Mind it, this depending on the value of these angles, for example, here this angle is say theta 0 1, this angle is, initial angle is theta 0 2, for another ray this angle, this initial angle for this ray is theta 0 3, and so on. The amplitude will also change, because in the amplitude I have sin theta 0. So, if theta 0 1 is less than theta 2 0, then there will be this ray will, this amplitude is small compared to that one, and also in the inside the period I have the value, because k is cos theta 0. So, that should also play a role in the period. So, that we need to find out. So, let us try to find out the period, because I draw that in just to show how this thing will look like, but at the same point we have to be careful about the period. So, period calculation, the period of the sinusoidal path I need to calculate, what should be the period, then I can rectify this. So, this figure, I think there is, I mean, when I draw a larger amplitude, then theta 0 is high. When the theta 0 is high, then in the period, if I look carefully, in the period k is sitting here. So, in the period what happened, the k value which is associated with this cos theta, this cos theta will decrease, because theta, if theta increase, the cos theta will decrease. If this is decreased, then I can have the period a larger period. So, that we will going to find out. So, let us do that quickly. So, this is the path, and for this path I have this theta 0 here. This is x and this is z, and the period is from this point to this point. this is the period actually, and I write this length as LP, because LP is the period of this sinusoidal ray path. So, simply LP multiplied by K should be 2 pi, because my path equation, it is sin kz. So, my path equation, let me write it once again. What was my path equation? So, x of z is simply I already evaluated, it is already there, I write it in this form, this one. So, period will be at z equal to LP, I have the period. So, my period LP will be simply 2 pi divided by K. Now, K value I already calculated here, the K is this one, root over of 2 delta cos theta 0 divided by A. So, I will put this value here. So, 2 pi, it should be 2 pi A divided by root over of 2 delta cos theta 0. Now, you can see the LP is a function of theta 0. So, LP is eventually a function of theta 0, that is the important thing. So, if I launch a light, with different theta 0, then LP, the period, will also going to change. If theta 0 is small, then I have a larger period. If theta 0 is large, we have a smaller period, and so on. So, for small launching angle, however, for small launching angle, this cos theta 0 will be nearly equal to 1. Then my LP will be 2 pi A divided by root over of 2 delta. Now, you can see when the launching angle is small, so that the cos theta 0 is of the order of 1, then this LP value become a constant quantity. It will not going to depend anymore with the launching condition. So, under such condition, what happened, all the rays will follow the same period. So, for small launching angle, so I can write it, I can draw this in this way. This is one ray. For nearly equal launching angle, I have another ray like this. For another launching angle, I can have another ray like with the same LP. So, if this is small, I mean very, however, according to my drawing, it's not looking as a it does not look very small, but if it is small, then what we find an extra information that LP for all the rays is constant, and whose value depend on only the value of the fiber parameter, which is the delta and A. It does not depend on whatever the angle, what angle I am launching, in which angle I am launching. In all cases, it will meet here and meet here. So, when the rays are meeting at same point, that means the dispersion value is less. So, that is an added advantage, that we can reduce the dispersion by making a refractive index profile like a parabolic profile. So, that if I launch a small angle, then these rays are having a almost similar LP. So, with this note I would like to conclude today's class. So, thank you for your attention. In the next class we will learn more about these ray paths, whatever the ray paths we have, that what should be the time it should take to reach certain points, and when the refractive index is constantly varying, then how it reaches to a certain point, what should be the expression, etc. we will going to calculate in the next class. With this note, thank you very much for your attention, and see you in the next class.